Let's talk about multi-hop big data pipelines today. In this day and age of Gen AI and machine learning, it is inevitable for businesses not only to maintain their own big data ecosystem, but also to ensure that it is scalable and performant. Hi, I'm Hardik Patel. I have around 20 years of experience in tech industry, working for both small startups and large enterprises. I hold master's degree in software engineering from BITS Pilani, and I have held various tech leadership roles at high-tech places like Yahoo, Symantec, Groupon, PayPal, to name a few. I have had opportunity to lead teams ranging from 5 plus people to 30 plus organization comprising of engineers, tech leads, and managers. I have over a decade of experience in designing and developing distributed systems and big data architectures. So before we dive deep into big data pipelines, let us first understand what are typical hops involved in such big data pipelines. It typically starts with data extraction. So as the name suggests, this is usually towards the intake side of data pipeline, and this stage is mostly involved in reading data from variety of sources, ranging from structured to semi-structured to completely unstructured data. The most essential aspect of this stage is to ensure connectors to disparate input data sources are resilient and there are sufficient data quality checks and to ensure no invalid data enters into the system, into the pipeline from the get-go. The second aspect or second hop in such data pipeline is data transformation. Besides cleansing the data, this stage is designed to format, normalize, and enrich data for faster processing, thereby reducing overall data availability lag through the subsequent stages of data pipeline. Data analysis is another important aspect of stages within the data pipeline. So once the data is cleansed and prepped up for faster processing, subsequent stages take up the responsibility of applying complex event processing and relevant machine learning algorithms to further extract meaningful insights in near real-time manner. The last aspect of a typical data pipeline is action and storage. So such data pipelines are essential in orchestrating automated responses to key events while also persisting processed data with optimized storage footprint. Now that we have looked at usual hops in a data pipeline, let us dive into various core design principles that are employed in building such pipelines. We will start with fundamental parallelism principle. So one of the key principles in such pipelines is parallelism. It is one of the fundamental tenets of such pipelines that help enable concurrent execution through means of effectively partitioning workloads across available computational nodes, thereby achieving maximum throughput. Scalability is another design goal, is to ensure we are able to elastically expand both horizontally and vertically in response to fluctuating and ever-evolving workloads of data volume and velocity. Fault tolerance is also inevitable in such complex environment of distributed systems and parallel processing. It helps us ensure we are meaningfully handling errors and also in some cases have automated recovery and self-healing mechanisms to ensure overall continuity of such data pipelines. Throughput optimization implies we are able to craft efficient data paths with minimal overhead of serialization, optimal memory utilization, and effective data partitioning to balance overall volume and velocity of incoming data. So now that we have looked at typical design principles involved in building these data pipelines, let us look at some of the very popular industry technology stack and tools and frameworks used to build such pipelines. Apache Kafka is an industry-leading messaging system. It is calibrated to handle more than 100,000 messages per second throughput with built-in capabilities of partitioning, replication, and fault tolerance. Spark is another very popular distributed data processing framework. It is 100 times faster than its in-memory Hadoop counterpart. Besides that, it natively supports SQL, machine learning models deployment, and graph data processing workloads. AWS Lambda happens to be the perfect technology that exhibits elasticity and is adaptable to ever-evolving and fluctuating data volume, velocity, and variety. It helps automatically scales from few requests per day to thousands per second and has a very attractive pay only for use pricing model. It is very popular amongst the companies and businesses operating in Amazon's AWS cloud. Apache Flink is yet another distributed data processing framework that supports constructs like exactly one semantics, event time processing, sophisticated windowing operations with sub-second latency. Now that we have looked at various technologies at use and different designing and developing big data pipelines, let us touch upon what are some usual performance optimization techniques in maintaining and ensuring that these pipelines are performant. So first strategy is caching strategy. Idea in case of caching strategy is to store frequently accessed data elements to further minimize redundant computation and disk and database IO calls. Data partitioning is another performance improvement techniques which is used to strategically segment datasets to enable parallel processing and reduce overall processing time. Load balancing is a means to dynamically distribute computational workloads to prevent resource bottlenecks and in turn optimize overall throughput. Resource allocation is a way to precisely allocate resources like CPU, memory, network based on workload characteristics and business priorities. The last one is optimized data formats, and it is a very popular technique to choose formats like columnar format, binary formats, which further helps us reduce IO operations and minimize data transfer overheads. So with that, now let's dive deeper into various scaling challenges and potential solutions involved in those challenges. So the first popular scaling challenge is data skewness. What is data skew? So it implies to uneven distribution of data, leading to performance and scale bottlenecks and resource utilization inefficiencies across clusters of nodes. A typical solution that we employ in order to tackle data skewness is to implement adaptive partitioning with real-time workload monitoring and dynamic rebalancing to ensure optimal processing across compute nodes. State management is another scaling challenge. What happens in case of state management is that with maintaining stateful operations, it significantly limits our ability to horizontally scale distributed system. So typical solution that we employ in this case is we actually deploy something like fault-tolerant distributed state stores with tiered caching architecture and configurable eviction policies. It helps us to preserve consistency while maximizing overall throughput at scale across various stages of data pipeline. Backpressure handling is another scaling challenge. This occurs when a typical high-velocity data producers ends up overwhelming a relatively slower consumer system. It actually leads to system instability and in some of the cases also leads to potential data loss. What a typical solution that can be employed in this case is to implement intelligent rate limiting algorithms, priority-based buffering queues, and adaptive throttling mechanism. This will certainly helps us maintain system equilibrium and at the time of varying data loads. Now let us look. So whenever we are talking about big data pipelines, you cannot avoid talking about observability. So let's touch upon a little bit of monitoring and observability. So how do we ensure that all of this complex ecosystem and distributed compute nodes and storage nodes are always observable and we always are able to stay on top of anything that is happening under the hood? So what are various ways to achieve effective observability? So one of the popular mechanism is metrics collection. Metrics collection is inevitable to track mission critical performance indicators like end-to-end latency, throughput at each and every processing stage, and resource computation trends. So when in case of metrics collection, it not only helps us track the effective and metrics in a meaningful way, but it also helps us stay proactive in case something goes south. The second aspect of observability is log analysis. So we capture detailed event logs as another aspect of keeping systems observable. It helps us identify error trends and improves our overall time required to conduct root cause analysis in the event of various performance issues. dtrace helps engineering teams to create correlation amongst distributed computed nodes and helps us ensure in taking preemptive action before performance degrades of this typical big data pipelines. So now with that, let us take a look at what are some of the key takeaways of this session. So architecture matters. To employ architectures that facilitates these performance criteria is inevitable in case of distributed systems and big data pipeline. Technology selection is another important aspect which helps us ensure that we are leveraging the right framework or tool for business problem at hand. Continuous optimization is also very important, which helps us regularly calibrate and benchmark key performance indicators to stay proactive with ever evolving data volume, velocity, and variety. Business alignment. This goes without saying. Whatever we build must be in alignment with impactful business outcomes. There is no technology solution without a meaningful business associated to it. I hope you enjoyed this talk as much as I enjoyed preparing for it. Thank you for your time today.